Hello everyone and welcome back. Now in the previous video I taught you a little bit about dynamic mode decomposition. And in this video I would like to continue my discussion about dynamic mode decomposition by first drawing attention to some of its weaknesses. And then introducing you to a method due to Dylewski, Coutts, and Tao, which is referred to as sliding window dynamic mode decomposition. So I'm going to start up with some demonstrations in MATLAB here. We're going to look at a problem case first, and then we'll look at how to overcome it. So let's start with a multi-scale signal. So I'm going to simulate a little differential equation here that I've built up, and I'm going to generate what's called a multi-scale signal. Okay, so what makes this a multi-scale signal? There are four components. There are four different pieces of the signal. Each one here is plotted. Each one is done in black. You can see that there's a fast, rapid oscillation taking place, and there is this slow background movement that's happening. This is very similar to what someone would see maybe with the tides. On a day-to-day basis, the tides go in and out twice per day. But due to gravitational forces from planets other than the moon, so say the sun, there is a slow drift, and when those tides go in and out, there's a background oscillation taking place that you wouldn't see if you just went, 1 or 2 days to the beach and saw high tide, low tide at the same time. But if you went one day at the first day of each month, you would start noticing that there's maybe a slow drift in when these high tide and slow tide take place. And that's what we're seeing right here in this multi-scale signal, right? So if we zoom right in on one component here, you can see this really sort of crisp movement taking place of just up and down. And then when you zoom out, you can see this really sort of long-term oscillation as well. And so what I'd like to do is I'd like to throw dynamic mode decomposition at this. Okay, so my data is 4-dimensional, so that's my capital M if you're taking notes from the previous video. And then capital N is just going to be, how much data I have in time. I create my DMD matrices from my data xdat. I create the DMD matrix. Again, just a pseudo-inverse computation is one line of code. And let's take a look at the eigenvalues and eigenvectors. And then let's try and make a prediction. Again, same thing that you saw in the previous video, just stepping forward in time by multiplying by A. So in this case, I'm only looking at a single piece of data. In this case, it's just the third component of my signal. And the only reason I've done this is just to isolate one specific example. All the other ones look exactly the same. I just want you to notice that the DMD prediction in red here looks very bad compared to the actual signal in black. So first of all, we can see that it starts off by doing a very good job in the short term, right? It's capturing the short-term oscillations very well, but very quickly it falls off. It misses these peaks and valleys quite badly, in my opinion. But the other thing is you can see a long-term offset happening. It's not getting the long-range signal frequency, and you can see these things are sort of falling off. And again, here you can see one of these peaks that it's sort of missing. So this might be good enough for your purposes, and if that's the case, stop the video now. But of course, we can do better than this, and I'm going to show you how we can do better than this as we proceed through this video. All right, let's lay down some of the theory here. Let's start by assuming that we have snapshots of data, just like the previous application for DMD, but in this case, I'm only going to think about sequential snapshots. So I want you to keep in mind that idea that I had going at the very beginning, that application into that multi-scale signal. So I'm just giving you, a whole range of data that's evolving through time sequentially. You can think of the snapshots, this is the first instance in time, second, third, fourth, and these things map through to each other. All standard DMD was looking for was multiplying matrix A by x1 to get x2, and then a matrix A by x2 to get x3, and then matrix multiplication to go all the way through. That's standard DMD. But what I'm going to do is I'm going to segment this data into windows. Okay, so I'm going to introduce a parameter here that's going to be called the window size. And as this probably sounds to you, I'm going to fragment the data into smaller snapshot windows. And I'm going to introduce this large data matrix. I'll call it X, and I'll put in brackets K here. This is meant to represent the kth window. And in this case, it's going to be xk, xk plus 1, so on and so forth, all the way up to xk plus capital T. And what this is this is a subsampling of my data, my snapshots here, starting at the kth snapshot and proceeding through one window's length, okay? Now, this is, again, a data matrix. This is in, if we're going to use R, it could be C. This is in M by capital T. Here, T is the size of the windows. And I'm assuming that my snapshots are in RM in the previous, as in the previous case, right? Now, what I could do is I could try to, for each K, so for each K, I could perform dynamic mode decomposition on these small windows. So I could do regular DMD to get a DMD matrix that linearly iterates me through this. Now notice I don't have a Y, so I'm going to use the next window up. So I'm going to define this to be x of k plus 1, right? That would be my Y associated to this thing. And then times the pseudo inverse of x of k. This is just applying DMD to the kth window. That's why I have this k up here. This represents, the kth window DMD matrix. This is linear time stepping through each window, okay? And for every single window, I can do the regular sort of DMD stuff. I can find, so I could find eigenvalues and eigenvectors, find eigenpairs of AK, right? That's what we were originally doing whenever we were doing DMD. The only difference here now is that I'm sweeping over windows, right? So it's a lot, it's a higher intensity of computations, but these are relatively quick computations that one can make on a computer based on modern numerical software. Then what you can do, if you're assuming that this is a multi-scale signal like I did in the previous application, that means that the eigenvalues should be sort of separated into different groups. Now, why is it that I think that? Well, I think that because if this is evolving on different timescales, there's a quick oscillation, maybe a slow background oscillation, maybe there's even another one in the background. Since motion in time comes from the eigenvalues of A, there should be one cluster of eigenvalues that's associated to fast motion, right? And there should be another cluster of eigenvalues that's associated to slow motion. Okay, so what I could do is I could try to separate these things out. I could introduce a threshold, so threshold, which I'll call lambda, to separate out the spectrum here. So to separate eigenvalues. Right, so for example, if you think about that signal that I gave you in the previous demonstration that was on the board here, m was equal to 4, and we had two distinct timescales, a big, long, slow one, and the fast ones. Now, you can think about these as being like sines and cosines. So there should be, the eigenvalues should come as complex conjugates. There should be two fast eigenvalues and two slow eigenvalues. That's sort of what I'm expecting out of this thing. And then, once I separate the eigenvalues, I can separate the signal inside the window, right? Because remember, these things are just linear superposition of eigenvalues and eigenvectors. So what I could do is I could take everything associated to the fast component and just keep those eigenvectors. And I could take everything associated to the slow eigenvalues and keep those. So separate into fast and slow components. Now, I know that I'm doing this without a whole lot of math because actually writing the math becomes a little bit complicated. I'm giving you this sort of algorithm here, and we're going to actually apply this in a moment. You'll see it demonstrated later on in this video. But now, since you've done this for every single k, for example, you've swept over all of the windows, you're sort of sliding your window across the whole data set, you've gathered up all of this information, you've collected fast and slow eigenvalues, what you can start looking for is macroscopic information about your signal. So for example, you could apply a clustering algorithm over eigenvalues in K, right? So think about what's happening here. If m is equal to 4, you get 4 eigenvalues every single window you do this. And you expect 2 of them to be fast and 2 of them to be slow. So if you have a whole bunch of windows that you swept over, capital K or little k here, then what you would want to do is sort of find the average of all of these fast and slow eigenvalues that you've computed over all of these windows. And that should give you something about the macroscopic dynamics. You know, what is the frequency of oscillation on the fast scale? What is the dominant frequency of oscillation on the slow scale? In our case, we're going to use k-means clustering, but there are all kinds of different ways to do clustering that you know, packages can perform for you in many different softwares. So it's up to you what you'd like to use. But that also means, you know, this is coming from number 3 here, but number 4 also allows you to separate the signal. You could separate signal into fast and slow components. Now, the way that you're sort of doing this is because you've separated into fast and slow components in each sort of window, you can take like the average over all the windows and put these things together. The way we're going to do this is with a mollifier. I'm going to show you. It's a sort of Gaussian function that slides across the windows here. But effectively what this will do is this will isolate the fast ground or the foreground quick oscillations and the background slow oscillations. And that means that, for example, if I'm trying to measure the tides over a long time scale, I don't care that they go in and out every day. I really just want to know when they start and when they end at, you know, a month, 2, 3, 4, 5 months from now, right? I don't care about that sort of variation of in and out. I just want to see that background drift that's taking place. All right, let's return to our numerical demonstration with that multiscale signal that we saw earlier. And let's apply this sliding window dynamic mode decomposition. So here I've set my window length. It's 1 over the sampling rate, dt in this case. I am going to sort of initialize a lot of these pieces here, and then let's sweep over the windows, okay? So this is the sort of beginning of the algorithm. Inside here, you can see what's being done is computing the DMD matrix for these matrices xk and xk plus 1. It looks ugly here, but it's not so bad. And then sort of standard DMD, compute the eigenvalues and the eigenvectors. In my case, I am, in order to sort these things, it becomes a little bit easier whenever you take the logarithm of the eigenvalues and divide off the time step. And then I've squared it to make it a little easier for me, okay? But this is all just sort of numerical work to make things look a little prettier. And then what I'm going to do, as I said, I'm going to look at the fast component, which corresponds to the eigenvalues that have, in this case, that are small. And then I'm also going to look at the slow component, which is the eigenvalues that are large in that absolute modulus that I've taken right up here, okay? So let's actually plot the results. Let's take a look at what's going to come out of this thing. And so here it is. I've plotted, remember I said that this signal is four-dimensional. There are four components to my signal. That's M. There are four eigenvalues. In this case, they come as two pairs of complex conjugates. So this is partially why I'm plotting the complex modulus, because they become sort of one eigenvalue. And effectively what you're seeing here is the lumping of these eigenvalues into both the fast and the slow component, okay? So what you can see here are a plot of the absolute value of these eigenvalues. This is in that logarithm plot, and then I'm squaring to make this more noticeable. You can see that one group of eigenvalues across all of the windows here is sitting very, very, very close to 0. And then another one is sitting very, very close to 100. Now, zoomed out like this, they look like they're all basically the same value. So that's why this figure right here is zooming you in. You can see that they're not necessarily perfect, but there's not a whole lot of fluctuation. And this is why we necessitate that clustering algorithm in order to sort of find the average of both of these clusters. In our case, we have two clusters. We can see it from the data. The red line that goes across these things is the mean of each one of these clusters. I used k-means for this, but if you have a favorite clustering algorithm, you're more than welcome to go ahead and use it. But we can see that it effectively, one dominant eigenvalue is about, sort of on average 100.0375, something along those lines, and the other one is about 0.02. Now these things are frequencies, so you can think about them as being like sine of omega t, cos of omega t, right? So these are 1 over the period. So in this case, these blue ones represent the slow scale motion, right? 1 over this becomes very, very large. And these green ones, they represent the fast scale motion, because 1 over this becomes very, very small. So again, here you can see fast scale, slow scale, clear delineation between these two things. And that's in part because I created the example that's going to be clear. But there are plenty of examples that I will link to in the description where things aren't as clear, but you can still get beautiful results out of them. Now here's what else I want to do. I want to reconstruct my signals over the entire time here. So what I'm doing is I'm taking the full time, each windowed solution, and I'm sort of averaging them together as I sweep over the time signal. And here, what you can see on the left-hand side here is the DMD signal in black behind, and superimposed in red over top is the actual DMD approximation. So black is the training data, red is the approximation. Take a look at this. We are hitting this very, very nicely compared to what you saw at the beginning of this video. This windowing is really allowing us to capture both the fast and the slow scale motion. And as I said, because DMD allows you to decompose data into linear superpositions of modes that either are moving fast or moving slow, this allows you to separate out the fast and slow components from your data. And this is exactly what I've done in this figure. In green is the fast scale oscillation. These are the fast pieces. Now you'll notice they're all sort of hovering around 0, because in order to get them to hover around the background, you have to add in that piece to the eigenvalue expansion. But here I just have the foreground motion going up and down. That's tides going in and out each day. And then what you can see in blue here is the very slow scale macroscopic background motion, right? That's the motion, that's the change in the tides from month to month. That is the background slow scale evolution. The stuff that I'm probably more interested in, because I would contend that, predicting on short time scales is very, very easy compared to predicting on very long time scales. So in this case, we have a way of sort of averaging out the fast scale oscillations to just get the trends, the macroscopic trends that are in the background here. And I'm going to leave it to you to go ahead and download the code and take a look at exactly what I'm doing in order to reconstruct these and separate these out. I didn't go into full detail here. You can always find that detail in the textbook, or you can find it in the code. What I would love to hear is if you're able to apply this to your own signals, if it worked, if it didn't work, if there was a problem. I would love to hear about it because I think this is a fantastic method. It is very powerful, as you can see from these demonstrations here. And it's relatively simple. Again, the heart is DMD, which is a matrix multiplication to find, another matrix that steps you through time. Very, very simple. So when we come back in the next video, we'll start talking about time delays and how they can complement places where DMD doesn't work well. I'll see you all in the next video, everybody.